All right, we're continuing our discussion of the hydrogen atom. We'll solve the Schrodinger equation today, Atkins 8a. So we should start with a picture, and I'm going to draw the hydrogen atom for you. Here is my nucleus. Right? It has a charge of +1, z equals 1. Hydrogen has 1 electron, right? And it's moving around with some kinetic energy. Right? There is also a classical potential, which is described here, 4 pi epsilon 0 over r. Right? It's negative because it's attracting it towards the nucleus. If this is our basic picture, right, we can start on our process. And the process for doing this is the same as it always is. I just got a message my battery was low. This might crash, who knows. So first step is to write the Schrodinger equation. H psi equals E psi. H is a Hamiltonian operator. It has a kinetic energy term. Right? And it has a potential energy term, B. C equals E psi. Now, what may or may not be obvious is that this is a system in which we want to work in 3D polar coordinates. So we're going to have coordinates r, theta, and phi. R is new to us, and I haven't shown that before. But it's simply the distance between the nucleus and our position, r. So you go back and look at your rigid rotor handout, and you will find the definition of del squared in polar coordinates. It's given here. Right? There's a second derivative with respect to the radius. And then there's this guy, capital lambda squared, which are all derivatives with respect to angular coordinates. We plug this in. Okay, we plug it, and we end up with this big, long, ugly expression. 1 over r, angular derivatives, potential equals E psi. How do we want to solve this? I heard it through cyberspace. We want to solve this with the separation of variables technique. Right? That is, we are going to take our wave function, which is a function of the coordinates r, theta, and phi, and we are going to set it equal to the product of a function which only depends on r, one which depends on theta, and one which depends on phi. This is worth doing. It's worth working through. It's on the worksheet problem for one of the lectures. I'll leave it to you to do it. But if you do that, you end up with these two expressions. Again, capital lambda were all those derivatives with respect to the angular coordinates, and they're operating on a function y. Y is the combined theta and phi functions. And then I get this expression for r. Which one do we want to tackle first? Again, I hear it through cyberspace. You're saying you want to tackle this one first. And that's a great idea because this expression is the same as that in the 2D rotation problem. Right? The rigid rotor. And what that means, in effect, is that the solutions are the spherical harmonics. That's why we give it the symbol y. So in terms of the angular motion of the hydrogen atom wave functions, the solutions are the spherical harmonics. We saw these before. So they have 2 quantum numbers, L and M. L runs 0, 1, 2. M runs L, L minus 1, L minus 2, ... to minus L. They have this mathematical form, and you're all experts at graphing these things now, so you'll know what these things look like. What I would remind you is that L dictates the shape of the orbital. So if I have an L equals 0, that's an s orbital. It's spherically symmetric. L equals 1 is the figure 8. L equals 2 is the clover leaf, right? So L is dictating the shape of this, and M is dictating the orientation. So if L is equal to 1, M could be 1, 0, or -1. There are 3 different orientations, which can be represented like this. Again, just like in the rigid rotor, the quantum number L determines the angular momentum of the electron. So it's telling us something about the momentum associated with the angular motion of it, given by this expression. And M determines the Z component of angular momentum. So Jz is given as mh bar. That's the angular motion. And I'm not going to belabor this point because essentially these solutions are the ones that you already know. All right, in the next video, I will talk about the radial solutions. See you then.